Right, hi folks. So, continuation of that theory we just did. Now we're going to apply this to hinges, and there's quite a lot to this. So, but once you've done one, you've done them all really. So we've got a uniform rod AB of mass 6 kg. So remember what uniform means. The center of mass is in the center. And length 4 meters is smoothly hinged at A, which means there's no friction. A light inextensible string is attached to the point at C, where AC is 3 meters. Okay, so let's just draw this out. So here's a wall, here's the rod, and this is A, and it goes on to B, right? It says it's got length 4 meters, it's got mass 6 kg, so that's 6g weight here. A light inextensible string is at the point C where AC is 3 meters. So that's 2 meters. And as you know, I like to apportion my sections so the individual meters are shown. And to the point D vertically above A. So that's D there, vertically above A, right? The string keeps the rod in equilibrium in a horizontal position, and the angle between the string and the rod is 40 degrees. So there's 40 degrees there. Find the tension in the string. Okay, so a few things to talk about here. A, this rod is going down, so where's tension going to act? Okay, we only care about forces on the plank. We know tension does this, but I don't care about the force on the wall. So just don't even bother with that. We're only interested on forces on the plank, okay? Which means that this hinge here at A, we need to be really careful we don't forget this. There has to be a reaction force at A, doesn't there? And there has to be a reaction force for a few reasons. A, this tension here has an element, a component going to the left, doesn't it? So therefore something has to be going to the right, otherwise it's not in equilibrium, right? So the hinge, we know, it makes sense, doesn't it, that the hinge is taking some of the weight and taking some of the pressure off that tension of the string. Now the question is, where's the force at the hinge? Like, which way is it going? Now, key bit of theory is that 3 forces in equilibrium, okay, always intersect at a point. Intersect. Okay? Really key bit of theory. So there is a force at the hinge, a reaction force, but where's it going to go? Well, if we follow the line of these forces, tension and the weight intersect here, and the forces are in equilibrium, which means that the reaction force at the hinge is also going to pass through that point. So I know roughly where it is. Now, is it going to go this way, or is it going to go this way? Well, it has to go to the right, because as I just said, there's a force, tension, pushing this thing to the left. So I have to have something opposing it. Do you see? So this is our RA, this is our reaction force at the hinge, and I only knew it was going that way because of that idea that the forces intersect at a point. Okay, so you have to use a bit of logic, and it's really helpful for that to happen. So the first part of the question now says, find the tension in the string. And remember these, the moments, this whole thing is in equilibrium, so the sum of the moments going anti-clockwise and clockwise are the same. So that's what I need to do. I need to do the moments now. And where am I going to take the moments from? Hopefully you're screaming out and saying, well, it has to be around A, because I don't know what RA is, right? I don't know what that is. And if I take the pivot at A, then the reaction, the force times the perpendicular distance from A, there is no perpendicular distance of RA from A, so that would just go. So all I need to worry about then is my normal theory. So let's do it. One's going, let's do clockwise equals anti-clockwise, right? So what's the clockwise forces? Well, that's that 6g. So line of action, 6g. Perpendicular distance from the pivot. So I've got 6g times by a perpendicular distance of 2. Likewise here, I've got my tension, right? Draw it going past the pivot. there's the pivot, so there's your right angle. That tells you exactly what you've got to do. So force is T, hypotenuse is 3, the distance x I'm looking for is opposite 40, so it must be sine, right? So hypotenuse sine 40, which means T must be 6g times 2 divided by that. So 6 times 9.8 times 2 divided by 3 sine 40. So 60.98 blah blah blah, but we always round, do 3 sig fig maximum because we dealt with G. Okay, so there's that. Now part B finds the magnitude of the reaction at the hinge. So we found tension, 61.0, right? But how do we find the magnitude and direction of the reaction at the hinge? Well, I know it's above that rod because I've drawn the green arrow that way and I've used logic to find that. But the thing you've got to realize is that RA is made up of a component up, across and a component up, isn't it? Right? So I'm going to call this component across. I'll just move that 2m out of the way. So 2 meters. I'm going to call this component across HA, and the one going up is VA, right? That's what makes up this RA. Because what I'm going to do is standard. I'm just going to resolve up and down and resolve left and right because it's in equilibrium. So what's all the forces going up? Well, we've got VA, that's the thing we're looking for, but we've also got tension. Tension can be put into components, can't it? It's up and across, yeah? So, or more helpfully, this is where your diagram can get a little bit messy. Tension is going across and it's going up, okay? So the up must be T sine 40 as its opposite are 40, yeah? And this all equals 6g. So VA must equal 6g, subtract T sine 40, and I know T is 61, okay? Well, I'm going to use the exact answer that I had before. So 6 times 9.8, subtract answer sine 40, I should get 19.6 newtons, right? And going across, what have I got across? So I've got HA going across, that's this one here. And what's opposing it? Well, it's tensions across this time. So we've used this component going up here already. That was our vertical component of T. And we've got HA going across to the left. We've got our horizontal one, which must be T cos 40. Now I appreciate my diagram is looking quite messy with all of these components and things, and it does sometimes help to draw a new diagram. So T was 60.98, so times that by cos 40, and we get 46.71, right? Blah 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 blah. But because we're trying to find the magnitude, we know from Pythagoras that's how we find the magnitude. We've got the across and up, but we want this RA one here. So Pythagoras says that RA, the magnitude of RA, is the horizontal squared plus the vertical squared. So we should get that thing squared plus 19.6 squared, square rooted, so 50.7 newtons to free SF, right? That's all good. And what's the angle? So there's the magnitude, but what's the angle? It says find the direction. Well, you can see from the triangle, if that's RA, here's our HA and here's our VA, right? We just need to do, if we're finding that angle, we need to do tan theta is VA, so 19.6 over our horizontal 46.71, inverse tan it, so theta must be tan to the minus 1, 19.6 divided by 46.7, so 22.8 degrees, and this is where you need to say above positive x-axis. Okay, so some direction on there, clearly stated. Let's try that again. Oh, that's the same slide. Let's try that again, and this time with a supporting rod. So a non-uniform rod, which as you know, means you don't know where the center of mass is. AB of mass 5 kilos and length 3 meters is freely hinged to a vertical wall. So I'm going to draw my wall. I've got my beam, AB, and supported underneath by a rod CD, where C lies below A and attached to the wall. Given the thrust in the rod is 35 newtons and AC is 1 meter, so C lies directly beneath A. So here's C, and its AC is 1 meter, so this is 1 meter here. And the angle between the rod and the vertical is 45 degrees. So you see I've got 45 degrees here. Find the distance of the center of mass from A. Okay. So the thrust is 35 meters. So notice it says thrust, because that rod supporting the beam is under compression, isn't it? The beam is pushing this thing down. I know it's 5G, but I don't know the distance of that weight. But thrust is going up through the rod. It wants to push the beam back. Okay? And like I say, I don't really care about the stuff affecting the wall. I only care about the stuff affecting the beam. And likewise, where there must be some reaction at the hinge. So what did we say? 3 forces intersect at one point. So therefore the reaction at the hinge must go through that center spot there. Now again, is it this way or is it that way? Well, it must be the one on the left, because the compression is going to the right and something needs to be opposing it. Okay, so this is my RA here, this way. Okay, cool. And my compression was 35 newtons. Right, cool. So same again. It says find the distance of the center of mass. The method's always the same. You're going to take moments around the pivot, and then you're going to resolve probably. Okay? Always the same when it comes to hinge problems. So moments around A, that knocks out that RA, so I don't even need to think about that. So let's do clockwise equals anti-clockwise, because it's in equilibrium, right? So clockwise first is this 5G. So I've got 5G, which is the weight, and I don't know what that distance is, so I'm going to call that D. Equals, and then I've got my force, 35 newtons, and remember it goes past the pivot point, so the pivot is there, so there's my right angle, and remember the angle in here is 45 degrees, so I need to know this distance D here. Well, actually I'll call it X. I need to know this distance X. Okay, there's D. So there's my right angle, like I say, or you can even look at the right angle there. Right? I know the diagram's looking a bit horrible now, but hopefully you can see. So that angle 45 is opposite the distance I'm looking for, and this is the hypotenuse of 1 here. So I've got 1, which is my hypotenuse, and it's sine 45 degrees, okay? Because x is opposite 45, so hypotenuse sine 45. So therefore, the distance of the center of mass must be that thing there. So 35 sine 45 divided by 5 times 9.8. So it's 0.505. Okay, meters. To 3SF, because we've used G. Okay? Find the distance in the center of mass of A. Fine. It could then say, find the reaction at the hinge. So why don't we make that a slight extension then? Find the reaction at the hinge, because it's exactly the same as what we did before. So reaction at the hinge, first we need to split this into horizontal, but notice the horizontal is going left now, and vertical, which is going down. Okay, so what do? We always resolve up and we resolve across. So to find RA, you resolve. To find tension or compression or distance of the center of mass, you take moments. So if we resolve up and down, down I've got VA and 5G, which is the same. But then this 35 newtons, like we know that's going across and up, okay? And if that's 45 degrees in there, that must be 45 degrees in there. So the one going up must be force 35 and sine 45 because this is opposite our 45. So we know our VA, and our VA is going to be 35 sine 45 minus 5 times 9.8. But this is what's great about this example, because you can see I've got a minus 24.25 here. Now, I shouldn't get minus because I thought I guessed that it was positive down and logic told me that, right? But this is the important learning point here. Because I didn't know what D was, right? If that's 1 meter here, then this is 1 meter too. So actually, D, we worked out, is 0.505, so actually it's about here. So my diagram, because how was I to know? You know, I had to guess. My diagram is actually wrong. Because the force thrust here, my 5G is here. So where do the forces intersect? They go here, here, and here, right? So that means the reaction force is either going that way or that way. But we've already established that as this component, your compression component, is going to the right, this one must be going to the left. So it is this way, okay? So there's our HA and there's our VA. So it's so good, isn't it, that the maths told us, hang on, there's a problem here. So actually I need to reevaluate my R up, okay? Because my R up is now VA is going up, right? But also this compression is going up. So it's plus our 35 sine 45 is the same as our 5G, right? The 5G is the only thing going down, and therefore VA is 5 times 9.8 subtract 35 sine 45. So that's much better. We got 24.25 whatever. Do you see? Really important learning point there, that because it was a non-uniform rod, I didn't know where D was. So my diagram actually gave me the wrong outlook. So left and right, what's going left? HA. What's going right? Well, it's our horizontal component of our compression, which is here or here, if you want to look at the old diagram. So we've got our force, and then it's cos 45, right? So therefore HA is 35 cos 45. So that's 24.7487, blah, blah, blah. And then how do we find the reaction? The magnitude, exactly. Square root of HA squared plus VA squared. Okay, so that is squared plus 24.25 squared. Oops. 24.7487 squared plus 24.25 squared square root. So 34.6, right, newtons to 3SF. And what's the direction? I'm so glad we drew that correctly now. So there's our theta. So if we look at that, here's RA, here's HA, here's VA. So again, we're saying tan theta is VA over HA. So 24.25 over 20, what's that, 4.7487. So tan to minus 1 of that, 21.25 divided by 24.7487 is 40. So implies theta is 44.4 degrees. Now, it has to be relative to something. So you're going to say above negative x-axis or something like that, all right? It has to have some relativity for the direction. So that's it for hinges. Let's go for ladders next.